Our speaker today is Hailun Zheng, and I'm very glad to introduce her. She's a collaborator and hopefully a future co-author, and she'll be talking about the reconstruction of simplicial polytopes.
Thanks for the invitation. And I understand that maybe not all of you are very familiar with polytopes, so I'm going to be slow in giving the definitions. If you have any questions, please stop me at any time. Okay, so what is a polytope? So the standard way to define a polytope is that we take the convex hull of finitely many points in the space. For example, if we have 5 points in R2 and we take the convex hull, so this is just a polygon with 4 vertices. And there's another way to define the polytopes, that is using Hall spaces. So now consider lines that are cutting the spaces into closed Hall spaces. And then we take the bounded intersection of closed Hall spaces. And this is another way to define the polytopes. It is not obvious that these two definitions are equivalent, but actually you could prove that these two definitions are equivalent. Okay, so we just take this as our definition, and we are going to define a couple of terms. The first one, the dimension of the polytope is just, the dimension of the affine span. And if the dimension is D, then we call it a D polytope. So for example, here you see these are just two-dimensional polytopes or just two polytopes. And also we are going to define faces of the polytopes. So how can I define it? So we have this polytope here, and then I'm going to take an arbitrary hyperplane. So in this case, it could be a line. And then, sometimes it will cut this polytope into two parts, but let's say that I have a hyperplane here, and then it's not going to, so one of the closed Hall spaces is going to fully contain this polytope. If this happens, then we say this hyperplane is good. But so in my case, in the previous case, the intersection of this hyperplane with the polytope is basically the empty set. But in some other cases, they're going to hit the polytope, say at a point, or along this line segment. And then if that is the case, we call this hyperplane a supporting hyperplane. And the intersection of this polytope P with this hyperplane is called a face, okay? And also, again, we could define the dimension of the faces. And then if the intersection consists of a single point, then of course, this is going to be a vertex of the polytope. If the intersection is one-dimensional, so it's going to be a line segment, and we call it an edge. And then sometimes, okay, so in dimension, let's say in dimension 3, okay, so we have another example, which is the tetrahedron. And the two-dimensional faces are sometimes called the facets, okay? All right, and then the next definition is that we could talk about the K-skeleton of a polytope. So this is gonna be a K-dimensional complex formed by all I-dimensional faces of P, okay? We just let K, if we just let K to be 1, and then one skeleton, based on this definition, means that it is gonna be a one-dimensional complex formed by the vertices and edges. So sometimes we also call it the graph of P. So one skeleton equals the graph of the polytope, okay? So in this talk, well, most of the time, hopefully, I will just talk about the one skeleton of the polytope. Okay, so finally, we could also count the number of faces in each dimension. So these are given by usually we call it face numbers of F numbers. So F0, for example, is the number of zero-dimensional faces. So that's the number of vertices, and you could also count the number of edges, etc., etc. And then these numbers are recorded, and then it will be called the face numbers. Okay, finally, this contains the combinatorial information of a polytope. So what happens is that we could actually form a poset out of this polytope. So we take the set of all faces of P, including the empty set and empty face, and also P itself, and we're going to form our face ladders. So how are we going to do that? Say we have a triangle. Let's say I have vertices 1, 2, and 3. And then the polytope is just going to be the triangle. And then if I order all the faces by inclusion, and then immediately we see this face ladders. And also the empty set. So that's kind of easy to see that this is the standard pose set that we have. And so what happens is that if you have a different polytope, let's say I have another triangle of different shape, and you see that although this could be realized, I mean, these two triangles are realized in the space and they have different shapes, but still they will have the same face ladders. This is good because somehow we want to distinguish different polytopes by just looking at the face ladders. So this is gonna be our major definitions for the polytopes. So now let's take a look at some examples. We say that the polytope is simplicial if all of its proper faces are simplices. So for example, in this picture, we see that they are all three-dimensional polytopes. So simplicial really means that all the faces are triangles or line segments or points. So if you look at this picture, this is going to be simplicial. The simplex is simplicial. And the last one, which is usually called octahedron or also 3-cross polytope, it is also simplicial. And another class of objects that we are going to look at are the simple polytopes. So we define it by looking at the vertices. So if every vertex is contained in exactly D facets, maybe I should say this is D polytope. Alternatively, you could say that if every vertex is of degree D, and then this polytope is going to be called a simple polytope. So now if you look at all these three examples, and the first one, the simplex is again simple because all vertices of degree 3. And the second picture, the cube, is again simple. So their graphs are going to be D regular graphs in general. All right. So now what we want to do is the following. We want to compare two different polytopes. As I said, you have two triangles, and they might have different shapes, but I don't want to distinguish these two polytopes by their geometric realization in the space, but rather their combinatorial type. So that motivates the following definition. We say that two polytopes are combinatorially equivalent, or you just say P is congruent to Q if their face lattices are isomorphic. So these two triangles are combinatorial equivalent by this definition. So now we have the major question for this talk. Let's say that I have a D polytope P. So I want to emphasize that assume that we know the dimension. So basically, you know that you have a polytope. You also know that the dimension of the polytope is D. And then I want to know how much information do we need to determine the entire face lattice of P. So in the face lattice, let's say this is P and this is the empty set, right? And then maybe I have something here. So these are the vertices of P, all the way to a couple things called the facets of P, right? This is going to be the entire face lattice. So the question is really about, can I just give you a partial set of this lattice? Say, I know the vertices, I know the edges of the polytope. Do they suffice to determine the entire face lattice of P? So of course, if you only know the vertices, that's not gonna be enough. Unless you have exactly D+1 vertices, and then you know that the polytope must be the simplex. But in general, if we have more than D+1 vertices, And then there are many polytopes with this given number of vertices, right? So at least it seems that we need to know something about the edges, okay? So in general, this question could be pretty hard because I think the only general result that we know is the following. Let's assume that the dimension is greater or equal to 3, okay? And then the only general result that we know is actually the following. The face lattice of a general D polytope, not necessarily simplicial or simple, is determined by its D-1 dimensional skeleton. In other words, if you know all the faces all the way to codimension 2, it's just that you don't know the facets. And then the information about the facets of the polytope can be recovered by all these lower dimensional faces. Okay, so that's a pretty nice result. It's just that it seems to be rather weak, right? Because you have to know a lot. You have to know a lot from this face lattice of the polytope. However, if you just consider some specific classes of polytopes, and actually it could be much nicer. So I'm just going to give you 2 classical results. And the first results are about the simple polytopes. So just think of the D-dimensional cubes, for example. So the theorem says that the face lattice of a simple D polytope is determined by its graph. Okay, so it does not work for many other classes of objects, but for this type of polytopes, it seems to be really strong. You just need to know the vertices, and you just need to know the edges, and then the 2-dimensional faces and some other higher dimensional faces could be determined by some algorithm. This is suggested by this theorem. Okay, and also there does exist an algorithm, especially you can find this algorithm in Kalai's paper, although it is not a very efficient algorithm, but it does solve the problem. Okay, so that is for the simple polytopes. But what about other classes of polytopes? Let me mention another result. So I'm going to define a class of objects called the sonotopes. So this is just a Minkowski sum of line segments. Okay, so Minkowski sum means that let's say that I have 2 line segments. Okay, so this is one line segment and the other one. And then given by this definition, the polytope formed by these line segments are just the sum of AI, BI, where AI is in between 0 and 1. So this is just a quadrilateral. Okay, so this is a sonotope. And for this class of polytopes, and we have a very similar result due to Bioner, Alderman, and Ziegler. They proved that the face lattice of a D sonotope is determined by its graph. Okay, so that's nice. But if you consider the other types of polytopes in general, they cannot be determined by its graph. So let me just mention our main objects today, that they are the simplicial polytopes. So now if you look at the simplicial polytopes, it cannot help that these 2 theorems work for simplicial polytopes. Why? Okay, I'm just going to give you a particular class of simplicial polytopes. Okay, so I have a polytope, let's say P, and this is defined on exactly n vertices. And then I claim that I have a definition that P is K neighborly if every K subset of V forms a face of P. So if you just plug in K equals 2, it just means that every pair of vertices in P actually form an edge of P. Okay, so this sounds to be a really weird property, but actually there are many K neighborly polytopes. So what I know is the following. So number 1, the first result about simplicial polytopes is that the face lattice of P is determined by its D/2 skeleton. So it has, well, this is a well-known theorem. So what happens is that if you have the face lattice all the way to faces of dimension D/2, and the higher dimensional faces, you could just use some topological argument to determine whether they are going to be missing or they are actually faces of P. So there's a very nice generalization to the class of triangulated manifolds. And the result is really similar. It's just that for manifolds, you have to be careful because if there's something, if the homology groups are really complicated, saying that the homology groups are not non-trivial in the middle, and then maybe just knowing D over 2 skeleton is not enough, but I think you just have to know a little bit more, say D over 2 plus 1 skeleton, okay? Using the same kind of proof, that is the topological argument. All right, so now that's good. For simplicial polytopes, we just have to know half of the faces, faces of dimension up to D over 2. But can I, just reduce this number a little bit? Say, what about D over 2 minus 1? And then this is not enough. We know that D over 2 minus 1 skeleton does not determine the combinatorial type of P. Why? Because we could just consider the K neighborly polytopes, okay, where K equals exactly D over 2. So we could show that there are many combinatorially distinct D over 2 neighborly D polytopes. So this might be really weird, but how many combinatorial distinct D over 2 neighborly polytopes are there? So let's say that I have n vertices, and then I know that here the combinatorial types, I should say types of D over 2 neighborly polytopes of dimension D is at least, I think the number is greater or equal to n to the D over 2 minus 1 times n. So that's a huge number. And all of them, they have exactly the same D over 2 minus 1 skeleton because they are neighborly, okay? So now you see the complexity of this problem. If I want to understand the reconstruction problems for simplicial polytopes, and you have to know a little bit more. Say, even if you know the D over 2 minus 1 skeleton, then you still have to find a way to distinguish all these neighborly polytopes, okay? So that's the reason why we have the following conjecture by Kalai. So he actually conjectured that what we need to consider is actually two things. Let's say I have a simplicial D polytope, and also I want to fix the number K in between 1 and the D over 2 plus 1. And then he conjectured that in order to determine the phase lattice of P, you have to know, of course, in this talk, we always consider some nice skeleton of P, so this time just K minus 1 skeleton of P. And the other thing is kind of mysterious. I'm going to define it later, but now I want to put it here. The other thing is the space of affine K stresses of P. So what is this space of affine K stresses of P? Just want to give you some motivation. This is just functions that we could define on a polytope. So, we could understand the spaces in two different ways, right? We could understand this vector space. We could also, alternatively, we could also define the functions on the vector spaces. So this is the second approach that we want to take, okay? We want to find a specific class of functions, which are called affine K stresses, such that, these functions capture the information of the facial structure of the polytope. This is the essence of these functions. But in order to define it, it's going to be pretty complicated. Okay, so let's see, what is an affine stress? So now, again, I want to say that I have a simplicial D polytope. Let's say that I have n vertices. And then what I'm going to do is using some algebraic tools to cook up functions defined on a polytope. So now for each of the vertex, let's say the vertices are given by 1, 2, all the way to n. they are in correspondence with some variables. Okay, let's say that the set of variables are just x1 all the way to xn. And now from those variables, I could form a polynomial ring over R. Okay. So if you know a little bit about combinatorial commutative algebra, then you know that I'm going to cook up the fixed ring, etc., but this is not what I'm going to do today. Now what I'm going to do is that, for all these vertices, okay, so I have vertices 1 all the way to n, they are realized in the space R to the D, right? And now I'm just write down the coordinates of all these vertices, okay? So here, this is the part of the matrix that I'm going to look at, okay? The columns of this matrix are exactly the vectors describing the positions of all the vertices. So this is for the vertex 1, vertex 2, all the way to vertex n, okay? And now I could actually form a couple of linear forms from these numbers, okay? This is just this matrix together with one additional line given by ones and times x1, x2, all the way to xn. Okay, so now I can write down explicitly what are these canonical linear forms, theta 1 all the way to theta d plus 1. So in particular, from this definition, you see that theta d plus 1 is always x1 plus x2 plus xn. Okay, just the sum of all the variables. But for the other theta i's, they have something to do with the realization of the polytope. Okay, so this is something that you want to remember. And finally, I will also want to define some differential operator. Okay, so now let's assume that I have an arbitrary polynomial, which is called lambda. And then I could define an operator, that sends this function, this polynomial lambda, to another polynomial of 1 degree. Yeah, so which is of the form that it is the sum of, okay, so what is the C of x? It is the sum of Ci times xi. So now lambda is sent to the sum of Ci times partial lambda over partial xi. Okay, so at this moment you might feel, okay, so that's really strange. Why do I want to do this? Okay, so let's do one example just to help us understand all the definitions. Okay, so the standard example that I'm going to take is the 3-cross polytope or the octahedron. So this is actually the regular 3-cross polytope. So if you begin with, writing down the canonical linear forms, just take note that this is a special realization of the cross polytope. So here, I just want to say that the vectors, let's say this is v1, this is v minus v1, and then v2 minus v2, and also v3 minus v3. Okay, I have 6 vertices, and then I write down their coordinates, and then this is going to be v1 minus v1, v2 minus v2, v3 minus v3. And then this will get me this matrix, just as what I did in the previous slide, okay? And the next step is, okay, so now I will be able to write down all these canonical linear forms given by this definition. So it's easy to see what they are, right? So for the variables, let's assume that, so v1 and minus v1 are corresponding to x1 and x minus 1. And same for the other 4 variables. And then the theta, remember that here d is 3, right? So I have theta 1 all the way to theta 4. And as I have already mentioned, the last one has nothing to do with this realization of this polytope. It is always the sum of all the variables, which is x1 plus x minus 1, etc., etc. But the other variables has a lot to do with the realization. So here I multiply it with the vector x1, x minus 1, x2, x minus 2, x3, x minus 3. I do this matrix multiplication, and then immediately you know that here, this gives me theta 1, theta 2, and theta 3. So immediately see that theta 1 is x1 minus x minus 1, etc., etc. Okay? So this is how we define the canonical linear forms. And in particular, again, I just want to emphasize that this has a lot to do with how you realize this polytope in space. And now, finally, okay, just to help us understand how to calculate this differential operator, how it works for an arbitrary function. Let's just say that I have a linear function, which is the sum of ci xi. And then what does it mean that the partial theta 1 of lambda is 0? So again, by the definition, so this guy, maybe just set it 1, is the sum of ci partial lambda over partial xi, right? So remember that for theta 1, it has nothing to do with the other 4 variables, s2, s minus 2, etc. So we just, look at this function and you see that if it is 0, then it really means that the coefficients for x1 and x minus 1, they have to be the same. So it really means that c1 equals c minus 1, okay? And then you could just check that, for the same reason, that the partial derivative with respect to theta 2 and theta 3 really means that the c2 equals c sub minus 2, etc., etc. Okay, very similar things. And then what about theta 4? And theta 4 really means that if you sum up all the coefficients ci, it is actually 0. Okay. Yeah. So for this particular example of the regulus recross polytope, and we see that somehow these expressions are very simple. These are very simple criteria to determine whether we have partial theta I of lambda equals 0. Okay, so again, I haven't explained why do I want to do this. So here, this is finally the definition of affine stresses. So you have to take note of a couple of keywords. So an affine I stress is always a polynomial. And again, it has to be homogeneous and it is of degree I. That's why we have an I here. And then, as I said, these are the polynomials defined on the polytope. So the first bullet point actually gives you have to capture the basis of the polytope. So I say that every term in this polynomial lambda, well, sometimes we call this support. The support of this term has to be a face of P. Okay, so just look at this example again. So this is V1 and this is minus V1, right? And then we know that here there's no edge in between them. Okay, so this line segment is actually in the interior of the polytope. So it really means that here lambda does not contain anything that looks like x1, x minus 1. So this is not possible for my 3-cross polytope. Okay, but on the other hand, it is possible that we have some non-square free terms. I mean that lambda is possibly something that looks like x1 squared times x2. Okay, it doesn't matter. Because here in this case, the support is on V1 and V2, and we know that V1, V2 is actually an edge in my polytope, okay? All right, now let's check the second point. The second point is kind of hard to understand, but the second result, second definition is actually lambda. When you take the partial derivative with respect to the linear forms from theta 1 all the way to theta d plus 1, it has to be 0. Okay, so this is something mysterious, and it's not straightforward to see why we want to have this condition, but actually this is just it has something to do with the properties of the polytope. In particular, the last one, it has a lot to do with the Lefschetz properties of the polytope that we are not going to talk about today. So the first observation is that these polynomials, once satisfying these two conditions, they would actually form a vector space. So for this reason, we want to give it a name, which is called the stress spaces. And this is going to be the notation, S representing stress, and I just It's just representing the degree of the polynomials. All right. And now we could do some calculation. Okay, so just to see whether we understand the definition, let's go back to the regular 3-cross polytope. And now for the 3-cross polytope, and I think I already explained that, so let's just plug in I equals 1. Okay, so now this first condition is kind of trivial. It just means that it's going to be a linear function on 6 variables, right? And now the second one is kind of important. We want to check that these partial derivatives gives me 0, okay? So now let's go back to this condition, right? We know that in order for it to be an alpha Y stress, and then we have to compare all the coefficients, and C1 equals C minus 1, and the C2 equals C minus 2, and C3 equals C minus 3, something like that. However, the last condition tells us that the sum of all these coefficients has to be 0. So easily you will be able to derive that the basis of the alpha 1 stresses are given by, it could be something like this, okay? x1 plus x minus 1 minus x2 minus x minus 2, and you just, rotate, the vertices 1, 2, 3, and to get the other one, okay? So that kind of, when you look at the spaces, you see that, okay, so there's nothing special. It's just affine dependencies on the vertices of the 3-cross polytope, right? Because now just remember that a regular 3-cross polytope have vertices plus or minus EI. So somehow the basis of affine 1 stresses are just about affine dependencies, okay? So this is in general, this is also true. However, the second one is not that easy. You could actually do an exercise at home to see that, okay, so for I greater or equal to 2, the regular 3-cross polytope, well, for this particular example, the affine 2 stresses, well, there's nothing, okay? There's nothing non-trivial. All right, so now this kind of suggests why we want to look at Kalai's conjecture. So his conjecture, let me just remind you once again, we have a simplicial polytope, we have a number in between 1 and d over 2 plus 1. And then he says that we want to know 2 things. One is the k minus 1 skeleton, the other one is the space of affine k stresses. And then, okay, as I already mentioned to you, that the space of affine 1 stresses describes affine dependencies among the vertices. So you know that the affine dependencies among the vertices actually will tell you almost everything about the polytope itself, right? You could basically recover all the information from that. So this corollary is this gives us this claim that the conjecture holds for k equals 1. And the other one, this is again not that trivial. So the second one is like the generalization of my observation from the 3-dimensional cross polytope. So in general, this is always true. If you have a simplicial polytope and the space of affine k stresses is always trivial for k greater than d over 2. Okay, so this is something classical result. So what does that mean? It means that, well, it tells you nothing if you look at the space of affine k stresses. And then it really means that the k minus 1 skeleton suffices, okay? So again, so in that particular case, Kalai's conjecture also holds. So now you see why he proposed this conjecture. So it's like an interpolation conjecture between these 2 well-known results, all right? So now, again, I want to mention why we want to look at these strange functions called affine stresses. So I'm just going to, say it very quickly. So it has a lot to do with combinatorial, combinate algebra, and Taurus varieties. So it has other meanings. In particular, if you look at the space of linear I stresses, I don't want to define the linear I stresses, but basically it just means that we don't have to consider the theta d plus 1 in the canonical linear forms. And this space is dual to the I squared piece of the Artinian reduction of the phase ring, okay? And the second one, I think I also mentioned about it. So you have this, the theta d plus 1 is really the left-chest element. Okay, so if you know the backgrounds of the story, you see what I'm talking about. Okay, the last one is kind of important. So for the space of affine stresses, not only we know how to define it, but also we know how to calculate it using the phase numbers. Okay, so it is exactly GI of P. So how do we define these G numbers? So you just have to remember these two numbers in this talk. G1 is the number of vertices minus 1 minus d minus 1. Okay, so that makes sense because you remember the space of affine stresses describe the affine dependencies, right? And the G2 is more complicated, but basically the G2 is defined by the number of vertices, number of edges, and it looks like this. It is highly non-trivial that the number of edges minus d times the number of vertices plus d plus 1 choose 2 is greater or equal to 0. It has to be because it is a vector space, right? But actually, if you know that these numbers are the dimension of some cohomology group for the Tauri variety associated with P, this comes automatically. Okay, so I just want to mention that these results are of interest to many people study polytopes. And that's the reason why it looks pretty nice that we could, solve some reconstruction problems by considering the affine stresses. Okay, so what we have proved is actually the following. We are not able to prove the conjecture in full strength, but we just consider some particular examples. So we proved this conjecture for the case k equals 2. So this means that the simplicity polytope is always determined by the graph of the polytope together with the space of affine two stresses. Okay, and the second class that we could prove is for the k-neighborly polytopes. Okay, so in the following time, maybe in the following 10 minutes, I'm just going to explain how do we prove the first result. Okay, so our motivation is really simple. It's just okay, so let me just call it a toy example. So the simplest polytope you could think of is actually the simplest. Well, what if you have so you have one more vertex, say you have altogether d plus 2 vertices for this d polytope. So usually we will consider the free sum of two simplices. So how do we define it? So what happens is that, let's say that in R3, I want to find two orthogonal spaces. One is a hyperplane like this, and another line which is orthogonal to it. And then in these two spaces, V1 and V2, I want to find two simplices, okay, containing the origin. So in this picture, I just want to find a triangle containing the origin, okay? And maybe for the other line, I just want to find a line segment, okay? So the free sum is that I take all these points on these two simplices, and then I take the converse hollow, okay? So here in my picture, I have 5 points. So this gives me this picture. A polytope with exactly 5 vertices. So this is the free sum of a triangle and a line segment, okay? So this is actually a nice example in the sense that, okay, I'm not able to draw the picture in dimension 4, but now let's just assume that k is greater than 2, okay, just to make sure that this property is good. So the first fact that you could find is that the only empty faces of P are the converse hollow B1 and B2. I'm just saying that these two simplices will be something in the interior of the polytope. This is really true in this picture, right? Because you know that the origin is actually in the interior of both this triangle and also the line segment. But of course, they are not going to be faces of P. Let me just say that they are empty faces. Okay, but actually their boundary, which is the empty triangle, the 3 line segments of this triangle is actually on a boundary of P. Okay, so now this is a very interesting result. We know that this polytope is actually k-neighborly. You could actually show that there's no missing faces of dimension, say 2 or 3 all the way to k. All right, so this is a nice result. And the second fact is that we always know how to find affine stresses. Remember that affine stresses are just affine dependencies among the vertices, right? And then now I have exactly d plus 2 vertices, and now there's basically one affine dependency. And here, the nice thing is that for some, you could just split the vertices into 2 sets given by V1 and V2. And you know the signs, right? There's only one possibility. So all these CIs, if on the vertices in V1, the signs are positive, and then for the vertices in the other set, it has to be negative. Okay, so this is a very easy observation. So what does that mean? It means that I've found this unique affine stress. But not just that, I could also define higher dimensional, I'm saying that affine K stresses from it. Why? Because I just need to multiply this function a couple of times, right? I hope that this is clear. If you multiply this function a couple of times, and then if you take the partial derivative with respect to theta I, that's okay. You always get 0, right? But you have to be careful. This function has to be defined on the support of P. You just have to make sure that all these terms are in correspondence to some phases of P, right? This is something non-trivial, but luckily we have this additional property that P is K-neighborly. So that's fine. All these terms of lambda I are actually supported in this polytope for every I less or equal to K. So now that's good. I find affine stresses, I find affine I stresses all the way to K, all the way to I less or equal to K. All right, so that's good. I have a full description of the space of affine stresses. So now I also find some philosophy behind the theme. So you see that I may have different realizations of the polytope, right? I may just draw this triangle and also line segment in different ways. And then the shape of the polytope is different. However, no matter how you draw this picture, the signs stay the same, right? The signs on V1 and the signs on V2, they are always of opposite signs, they cannot have the same sign. So I figure out that I don't need to look at explicit numbers. I don't need to look at affine stresses and I look at explicitly what are these C1, C2, etc., etc. I just need to understand the signs, okay? So now I want to define a sign vector, okay? So let's say that I have lambda, which is, say, an affine stress. And then in my example, okay, maybe I should draw it again. So this is my polytope, right? Okay. And 1, 2, 3, 4, and 5. And then I know that affine stress is always something that looks like this. I don't care the numbers. I just need to write down the signs. If the signs for 1, 2, 3 are positive and 4, 5 are going to be negative, or the other way around. These are the only 2 possibilities. Okay. So this is basically the vectors in VP of 1 in my example. Okay, so I have the following conjecture. I don't want to take the space of affine K stresses. I just want to look at the sign vectors, and the sign vectors captures all the signs that appears in every affine I stress in my set ST of K. All right. So this is my conjecture, and how do I prove it? I prove it in a very intuitive way, okay? So now, again, I want to take this example. Oh, this is a horrible picture, but anyway. Let's say that I have A and B. So in my polytope, A and B does not form an edge in my polytope. It's actually in the interior, right? Just think about it. If I add it back to the graph of P, and then, well, maybe I will be able to find some non-trivial affine stresses. This is actually true, okay? So now assume that I have a missing edge, and then I show that if you not only consider the graph of P, but also additional edge AB, And then we'll be able to show that it is always possible to find a stress such that the sign on AB is plus, and then the sign on the other three edges that are incident to A, and their signs are going to be negative, okay? And then if this happens, and then we'll be able to identify the missing edge, okay? This is how we do it. Then how do we identify the missing edges? Because once you'll be able to find all these orphan-2 stresses, and then I'm going to use this information to determine the missing faces. Just think about this picture, okay? So 1, 2, 3 are the other 3 vertices. Just think about it. I have a non-trivial orphan-2 stress, lambda. And then what I'm going to do is I'm going to take the partial derivative with respect to XA, with respect to this vertex. And if this pattern works, you see that here plus and minus, 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 and then this will look like SB minus S1 minus S2 minus S3. Somehow it suggests that, okay, this edge A and B will cross some point in the relative interior of this triangle 1, 2, 3. So basically that is the idea. And also you could generalize it to some higher dimensional cases. Okay. So yeah, so that's basically the proof. Actually, once we finish the paper, and actually Kalai suggested following strengthening of the conjecture, he said that maybe if you consider a simplicial polytope without empty facets, and then the graph of P together with the space of orphan-2 stresses will actually uniquely determine P up to orphan equivalence. So this is just a strengthening. Okay, we don't know how to prove it. I think it is true for true neighborly case, but this is really easy to see that. So yeah, that's it. I will stop here. Thanks for your attention.
Let's thank the speaker. That was wonderful, Hailun. Do we have any questions?
I have one question.
Yes.
So when you were defining the stresses, I think by slides like 8 or 9, if you take the 1 stresses, that's very close related to how you construct the Gale transform of the polytope.
Yes.
Is there an intuition of like, so the Gale transform usually gives you other polytopes that allow you to understand the one you started with. If you do this for 2 stresses or 3 stresses, does it also give you polytopes which are interesting to understand for the original one, or?
Well, I only know that orphan-1 stresses are basically, as you said, the Gale transform of the polytope. But for the higher dimensional analogs, I don't know. I don't see there's a direct relation to get it back.
Are there any more questions?
Yeah, I have a question. So
Yes.
This isn't really about your work, but it's a more general question that maybe I should know the answer to. But so knowing the, to know the K skeleton, it's actually enough just to know the incidences between the vertices in the K bases in the simplicial case. So it raises a question to me of whether it makes sense to ask more generally, not just for whether a K skeleton determines the face lattice, but whether some particularly rank selected poset of the face lattice determines the whole face lattice. And do you know if there's any results on that more generally?
No, not that I'm aware of.
Should we thank the speaker again? I'll stop the recording.